So I shall speak about our very recent work made jointly with Denis Borisov from St. Petersburg. He works in ITMO University, and also with Miloslav Znoil from Czech Republic, and he works in Nuclear Institute of Czech Academy of Sciences. And I begin with a very simple example just to give an idea what kind of problem I'm going to tell about. And the simplest example actually is the following operator. It's a Laplacian in R2, and it has two potentials. The first one is V0, and it depends only on one variable, and the second term is multiplied by epsilon. It's some arbitrary potential which depends on both variables. And just for further purposes, I rewrite this Laplacian as it's defined. And I assume that V0 and that both these functions are some smooth potentials. And in addition, we assume that W is completely supported, and also the potential, this potential can be complex valued. For V0, I assume that actually it's smooth, it can be unbounded even, but bounded from below. V0 is real valued, and the second term is regarded as a perturbation of this operator. So epsilon is a small positive parameter. So the main feature of this operator is that this unperturbed potential, this V0, that it depends only on x. So in a sense, so this part actually, in a sense, it's a one-dimensional operator, second derivative plus V0, and then we just add the second derivative in y. So this can be regarded like we have one dimensional operator with potential V0, but acting on a plane, and to have its well defined, we just add the second derivative. And what we do after that is that we add some small perturbation which actually which mix the variables x and y, and we ask what is the spectrum of such operator when epsilon is small. So if epsilon is 0, if we don't have it, then actually you see easily that the spectrum of such operator, I mean this one, the limiting one, can be found explicitly just by separating variables x and y. I shall show later how this can be done. And once we add this perturbation, we just mix these variables, and we cannot make this separation anymore. And the question is actually how such small localized perturbation can influence the spectrum. So this is this one-dimensional operator on the axis. I mean, it's the second derivative plus this potential. So it's h prime. It acts on axis first. And I assume this will be my main assumption, that the spectrum of this operator below some constant consists of finitely many discrete eigenvalues, which are lambda 1, lambda 2, and then up to some lambda m. And all these eigenvalues are less than some constant c. And what's going on after these constants, I don't know. And actually, I don't care how the spectrum looks like. So I just say that the lower part of the spectrum is very simple. It's just finitely many discrete eigenvalues. And after some point, how this spectrum looks like is not important.
Excuse me, what is the reason to require epsilon to be positive.
Well,
W is complex value.
okay, this is for simplicity, because later I shall check some. I shall make some tests. I shall have some conditions, and for them I shall need that epsilon is positive. It means that all this complex value is inside this potential. So you can first say that epsilon is complex valued, but then move this complexity inside the potential. And actually, if you say that epsilon is complex valued, then I tell you that instead of epsilon, check the absolute value of epsilon and move the rest into the potential. This of course, epsilon can be arbitrary.
C is not zero.
But V0 can be arbitrary. It can be growing, it can be also negative. So the V0 in general, V0 looks something like this, and here is X. It's like this. But of course, this is all up to shift.
Denis, do you require that lambdas are simple eigenvalues?
No. It can be multiple actually, but here since it's one dimensional, I just know that all of them are simple. But later I shall have the general model in a multi-dimensional case, and then there can be multiple eigenvalues. So if I put these eigenvalues on the complex plane, so these are just some real eigenvalues on the real axis. And then if I return back to this operator, then for this operator, I shall have an essential spectrum, which shall look like this. So for one-dimensional operator, I have just discrete eigenvalues, but once I add the second derivatives, whole this half line is filled by the essential spectrum. And the first statement here is that the essential spectrum of both this operator and that one, it's a half line from lambda 1 to plus infinity. And inside this essential spectrum, I have a certain special point, these discrete eigenvalues, and I shall call them thresholds. And the main effect is that once I add this perturbation, I see that certain eigenvalues and resonances can come from the edges of from the bottom of the essential spectrum, and also from these points lambda 2, lambda 3, etc. So these special thresholds in the essential spectrum, they bifurcate into eigenvalues and resonances once I add some small localized perturbation. So without epsilon, I have just essential spectrum, which is this red line. Once I turn on this perturbation, I have eigenvalues or resonances. And my aim actually here is to understand what I can say about such eigenvalues and resonances, how they behave when they exist, what is the asymptotic behavior, how many eigenvalues and resonances can emerge. And so the main aim is to study this effect. But the matter of this effect is that without perturbation, I have only essential spectrum. Inside this essential spectrum, I have special thresholds, which come as the eigenvalues of this one-dimensional operator. And when I come to the plane, when I add the second derivative, and when I mix the variables via the perturbation, what I see are the additional eigenvalues and resonances. So the aim is to understand how they behave when they exist, and all the questions of this kind.
Called a green cross and the
I can have green eigenvalues, and also I have purple or rather magenta resonances. And near each threshold, I can both eigenvalues, I can have eigenvalues and resonances. And actually, we are able to describe quite in all details what kind of picture I have in near each threshold to count and to understand what kind of object I have here and to calculate the asymptotic expansions for this object with respect to epsilon. And actually, we can do it in a very general setting, not only for the potentials, not only in the case when the perturbation is just a potential, but also for a very general perturbation, and not only in R2, but in very general domains. But the main matter actually of a problem that actually we have something which is some operator which acts on a domain or the less dimension, then we add one more derivative, and when we add a perturbation. These are the main features. We have some operator H prime, then second derivative plus perturbation, and then this picture will be kept, and this one will be kept as well. So actually, the main features are seen already on this simple example, but they still preserve also in the general setting. General setting is as follows. So we begin with some omega, which is an arbitrary domain, which can be both bounded or unbounded, and it lives in R d-1. It's d-1 dimensional, and in this domain we define some operator H prime, which is of a general form. It's a second order differential operator, which is self-adjoint, and it acts in this omega. And I assume that the coefficients of these operators are just some smooth function. And on the boundary, I just impose some classical boundary conditions so that this operator, operator with this boundary condition is self-adjoint. And so the form of a boundary condition can be, say, like this or this one. So it can be the first boundary condition of a Robin type. But in the case of this boundary condition, I also assume that these coefficients also depends only on x prime. And other cases of the boundary conditions are also possible. So the only thing we need is that this operator with this boundary condition is self-adjoint. And then I go to a higher dimension, namely I introduce a cylinder, which is for which this omega is a cross section. And in this big omega, I introduce the operator, which is actually the same H prime plus second derivative. This is exactly what I said. So as H prime, I can choose arbitrary operator, but for the H, then I just add one more second derivative. And I keep the same boundary condition. Then I know that this operator is self-adjoint. So actually, this H is my limiting operator in omega. And just to show some pictures, so if I have some cross section, say if it's bounded, then it looks like this. Then I go to a cylinder omega, and on this cross section I have H prime, and on cylinder omega I have H. I assume that the lower part of the spectrum of H prime is again formed by the discrete eigenvalues, which are located below some constant C0. And again, I don't care how this spectrum looks like after this constant. And then I shall also need some eigenfunction associated with these eigenvalues. So this is the main assumption for the H prime, which acts on the cross section, namely on omega. And again, the same picture. So for the H prime, I have just discrete eigenvalues. And when I come to H, then I have here essential spectrum. I have here again bottom of this essential spectrum at lambda 1, and also I have some thresholds inside this essential spectrum, which are lambda 2, lambda 3, and there can be multiple eigenvalues. Say lambda 3 can be equal to lambda 4. And so I still don't have a perturbation here, but just in advance I say that I shall add the perturbation of such form which are localized so that they don't change the essential spectrum. So they can just they can just produce eigenvalues and resonances from the thresholds. So this H prime and H, I recall that it looks like this. This is actually my limiting operator, and what I'm going to do now is to introduce the perturbation. So in the simplest example, this H was just the Laplacian plus V0. I say that I can add much more term, and actually it will also work. Now about the perturbation. So the simplest perturbation is of course by the potential, which as I shown. But of course, if we think a little bit, we can also think about perturbation by some differential operators. We can add not only the potential, but also we can add derivatives with compactly supported coefficients. This is also doable. This is also possible. The next idea which comes in mind is that we can add not only differential operator, but also some integral operators with compactly supported kernels. Then other ideas can appear. So in order to be quite general, I just assume that the perturbation is made by some abstract operator, which just is of the following form. And each of these operators L, L1, L2, L3, and this L itself, these are just some bounded operators which act from W22 into L2. And as operators acting from W22 into L2, they are bounded. Of course, they are unbounded as acting in L2. But as acting from W22 into L2, they are bounded. And why I have here W22, this is just to include into this scheme the second order differential operators. Now about these weights. So these operators act on some weighted spaces, and actually these are very rigorous definitions, but you don't have to go into big details and to try to understand what is the nature of these spaces. The idea is the following. So I have here exponent with minus. It means that actually the function which lives in this space, they can grow at infinity, even exponentially fast, and how fast they can grow. It's so the border is this theta. And the function which lives in L2, here I have exponent with plus. It means that they should decay exponentially. So my idea is that all these L1, L2, L3, they should map growing function into decaying ones. This is how I understand the localization of my perturbation. if we think about the compactly supported potential, say as I showed in the beginning, then if I have a growing function, when I multiply it by the compactly supported potential, then of course this outside it support I shall have just 0. So, but I can even generalize in this sense the notion of being localized. So my abstract operator is localized if it maps growing functions into so exponentially growing functions into exponentially decaying functions. And also I don't assume that these operators are symmetric. They can be arbitrary. So let them be arbitrary. And actually, this is the picture which shows how this L epsilon acts. So I have something which goes exponentially, grows exponentially fast at infinity. And after the action of L epsilon, I have something which is actually localized in the sense that the tails are exponentially small. And then the perturbation of my operator, which is actually H epsilon, it's this operator H plus epsilon times L epsilon. And since these are not symmetric, my H epsilon is not self-adjoint. If they are symmetric, then of course this operator will be self-adjoint, but in the general case, this is not the case. So now the question is what's going on with the spectrum when I add this perturbation, and the first answer is as follows. So as I said, so I can have here a general structure of this threshold. So let me first take one of them. Let it be an n multiple eigenvalue of this operator H prime. And in order to speak about the resonances, I first should define rigorously this object. If we want to speak only about eigenvalues, then of course it's simple. So eigenvalue of an operator is a number for which this equation have a non-zero solution, which is inside which is inside our space. But for the resonances, it's not so simple. It's not so simple, and the way how I define it, it's a standard actually way, the corresponding meromorphic continuation of a resolvent. So the first main result says that in the vicinity of each this lambda 1, lambda 2, lambda 3, etc., I can construct a meromorphic continuation R epsilon t, which is a meromorphic continuation of a resolvent acting on this weighted space. And this continuation with respect to K is meromorphic, and we have this identity saying that so it's true for when K is such that the real part is positive, and for the imaginary part of K squared, we have this inequality. Actually, this tau here can be a plus 1 or minus 1, and it actually means that I have two meromorphic continuations in the vicinity of each threshold. As if we are at the bottom of that spectrum, then actually these two continuations coincide, and this actually just one continuation. But for the other threshold, I have two different operators I epsilon tau, and the difference between them is that one is from the upper half plane into the lower one, while the second one is from the lower half plane into the upper one. for tau being +1, I go from the upper half plane into the lower one, and here I go in the opposite direction. So the first continuation acts as follows. So on the upper half plane, it's actually the resolvent. When I go through the essential spectrum, and here I have just another operator which is not a resolvent anymore, but the dependence on this parameter k, which actually changed when I go like this, the dependence on this k is analytic. And then I can also go from the lower half plane into the upper one, this is quite a standard thing for the self-adjoint operators, and the resonances are defined usually as the poles in K for such operators. So we make these two continuations, and then we say that then we should look at the poles of these two operators, and these poles are actually either eigenvalues or resonances. These are eigenvalues if the corresponding eigenfunctions are inside W22, and these are resonances if this is not the case. For the self-adjoint operators, usually just one continuation is constructed. As far as I remember, it's from the upper half plane into the lower one, right? Usually, if the operator is self-adjoint, usually one deals only for the case tau being +1. The reason is that for this operator, for some operator H, when we then study the evolutionary equation, then only the poles of +1 appears. So here, only the poles of this continuation are important. The other poles are not seen. This is for the case when we have a self-adjoint operator. But once this is not the case, as in my case, this is no longer true. And this is why here I deal with both cases tau being ±1, and as I shall show very soon, this is actually very important in this problem. And as I said, the resonances and eigenvalues are the poles of these continuations. These resonances and eigenvalues are expressed in VK by this formula. And again, as I said, the difference between eigenvalues and resonances is the behavior or the associated eigenfunctions at infinity. They either grow exponentially when it is resonance, or they exponentially decay, and then this is an eigenvalue. The next result is about the poles. So actually, our answer is quite general, and it involves plenty of formulae. But now I show just a part of them, just to get an idea how they look like. And the first answer is as follows. So we should calculate the following matrix with such entries. And actually, this is the leading term of the perturbation theory, which is very common. So I have limiting eigenvalues, I have perturbation, and when I act by the perturbation to one limiting eigenvalue and calculate the scalar product with some other eigenfunction. And then I take the matrix. Of course, what I should do then is to calculate the eigenvalues of this matrix. So in general, I have some eigenvalues, mu I. They are different, and so these are different eigenvalues, and for which eigenvalues I have some multiplicity. Since I don't assume that L1 is not, we don't assume that L1 is symmetric, then actually this is a very general matrix which is not self-adjoint, and these eigenvalues are in general complex valued. And then the answer is as follows. So fix tau. Then find the eigenvalues. Then for each tau, each of these continuations possess exactly n poles. And for each of these poles, I have the following asymptotic formula. So when I say, so n is the multiplicity of this threshold. This is the size of this matrix. But when I say when I say that I have n poles, then I take them counting their orders. Order. So if it is a pole, then it has an order as a pole. So the sum of all these orders is n. Of course, for each such pole, I have an associated eigenfunction. The number of associated eigenfunctions is a multiplicity of this pole. And in general, the multiplicity is less or equal to order. For the self-adjoint case, I know how to prove that the multiplicity and order is the same thing. For the non-self-adjoint case, this is not the case. Roughly speaking, this is because in the non-self-adjoint case, I can have some Jordan blocks and associated functions, and this is why the geometric multiplicity is less than the algebraic one. So, nevertheless, in a general case, if I have a pole, if I have a threshold of a multiplicity n, then I have exactly n poles for tau being +1 and for tau being -1. So in general, near each threshold, I have two sets of poles. The total number of them, if I count their order, is 2n. I have n poles for tau being -1 and n poles for tau being +1. In general, I have 2n poles. If all of them are simple, it means that in general, I have twice more emerging objects twice more in comparison with a multiplicity of a threshold. So in the limiting case, I have just a threshold and I have n associated eigenfunctions. Then I add a general perturbation, and these n eigenfunctions produce 2n eigenfunctions. So that the multiplicity of all poles is in general greater than the multiplicity of a threshold. So in a sense, this is like additional objects coming from nowhere. In the limit, we have less multiplicity than after the perturbation, and we can actually have up to twice more objects. And in particular, if this threshold is simple, then under perturbation, simple thresholds with just one associated eigenfunction can produce two eigenvalues, one in the upper half plane, one in the lower one. This is, in a sense, in a conflict with the usual idea that the total multiplicity under the perturbation should be preserved. And this is one of the examples when we shows that this is just that this is not a rule, this is not a law, and it's possible in some examples to have extra object, to have extra multiplicity produced just by the perturbation. In the end, I shall show just one simple example where when this effect is just visible. And then once I have the pole, the next question is to understand whether this pole produces eigenvalues or resonances. This is so from the point of view of pole, so these eigenvalues and resonances are actually the same. And to understand whether the associated eigenfunctions decay or grow, we should know a little bit more about the behavior of these functions and about these poles. So we can solve also this issue as follows. If we look at the bottom of the essential spectrum, when we fix some mu I, then I take the poles with this with such expansions. If the real part of this mu I is positive, then each of these poles produces an eigenvalue by this formula, and I can even find the leading term in the asymptotic expansion for these eigenvalues. They look like this. If the real part of this mu I is less than 0, if for a fixed I, if it's a negative, then this pole generate a resonance, and the formula is the same for this resonance, and it's even the same as with the same expansion. For other thresholds, the answer is as follows. If I take some mu I, if the real part is positive, then I should fix tau, and then I should take this in this condition. If this is the case, if both of them hold, then the pole produce eigenvalues by the same formulas with the same expansions. If the real part is negative, and if this one is negative, then it's not important whether I have then the imaginary part is no longer important. Then this pole produce a resonance. And if the real part is positive, but here I change less by greater, and then I add also some technical conditions which actually are true in a general case. So they're really quite, they're really of a very technical nature. Then the same pole gives rise to a resonance. So in this case, I have eigenvalue. In both these two cases, I have resonance. It means that for as p is greater than 1 for the threshold inside of the essential spectrum, for each tau, I can have a set of poles, and these poles are either eigenvalues or resonances. And for each of these sets, and so I have actually two sets, and the total multiplicity can be twice more than the multiplicity of a threshold. And this is exactly the same picture, so as was in the beginning. So in the vicinity of the bottom, actually I have as many eigenvalues and resonances as the multiplicity of the bottom. So if this bottom was simple, I can have here either one green eigenvalue or one magenta resonance. Because text says that this is magenta, the color is called like this. For here I can have, say, double threshold, and it gives rise to one eigenvalue and one resonance. Here, for instance, I can also have a double threshold, but it gives rise just to one resonance. As I said, in the non-self-adjoint case, the total multiplicity can be even less than the multiplicity of the threshold. But for instance, here, this shows the case when I have here a simple threshold with just one associated eigenfunction, and it gives rise to two eigenvalues. This is exactly the case of doubling multiplicity under the perturbation. And this is actually the one or the main features of this some result. So under the perturbation in this model, we can have twice more eigenvalues and resonances. And the explanation for this effect is simple. The point is that here I have to deal with both meromorphic continuations, not just with one, as here, as for the self-adjoint case. But for the non-self-adjoint case, in general, I have to deal with both of them, and each of them has its own poles. and when we count all these poles, we actually see such nice picture. We have twice more eigenvalues under the perturbations. And to show a very simple example when it is possible, I just consider a PT symmetric waveguide. So PT symmetric operators, now it's a kind of, not a kind of, but it's really a hot topic. These are quite simple operators, but they appeared very, like many years ago in works by Crane. But it was something like operators acting on the spaces within definite metric. When the scalar product is degenerate, and it was some abstract theory. Then
It was from physics, like parity time, right?
yes, it's parity time, and actually maybe in the end of the last century, something like in 98, in 2001, in 2002, there was an additional interest to such operators. It came from the work by Karl Bender with Kofos, who showed that if you have this property for such operator, then it can have a real spectrum. It's non-self-adjoint, but it has real spectrum. So in a sense, they found a class of non-self-adjoint operators for some of the operators in this class, they were able to prove that the spectrum is real. And the idea was to construct some analog of quantum mechanics for such operators. So since they have real spectrum, they have real energy, and maybe there is some quantum physics behind these operators. The answer was no, this is not the case. But maybe in 2010, something like 10 years ago, it was found that these PT symmetric operators appear in nonlinear optics. And physicists, once they realized it, they started working with these operators very intensively, and now there are plenty of papers on this subject. So this was the motivation for my PT symmetric waveguide. This is actually a strip, the usual. So let me just show it. So this is a strip in R2 of width pi. Here I deal with the Laplacian. Here the first boundary condition. And in my case, H prime is just, so if here is x and here if is y, then H prime is d over y squared on 0 pi, subject to the first boundary condition, u0, use u0 of pi. Of course, the eigenvalues of these operators are very simple. These are just p squared for all p being 1, 2, 3, etc. And the associated eigenfunctions are just as it is written. It's sine pi y. I have here x1, x2, but it doesn't matter. So then the perturbation which I add is just a potential of this form, and it's a complex valued potential, and the main feature is that the real part is even with respect to, so to be understandable, y is x1 and x is x2. So the real part is even in this direction, and the imaginary part is odd in this direction. This is actually so these two conditions says that I have this PT symmetry. Actually, it means that if in this operator I change x2 by minus x2, and then if I take the complex conjugation of this operator, I get the same H epsilon. And our results for this model say the following. If we are at the bottom of the essential spectrum, which starts now from 1, so I have here, if I take here P equals to 1, then lambda 1 is 1. And near the bottom, I have either one eigenvalue or one resonance. In both cases, it behaves like this. And the difference is that for the eigenvalue, I should have this in this condition, and for the resonance, I have that one. So I take W to 1, calculate this integral, and then I check the sign. And if the sign is positive, then this is an eigenvalue. If it's negative, then it's a resonance. For internal thresholds, I should first check this condition, and then I should check that one. This one is for the real part, and that one is for the real part and for the imaginary part. If both of them hold, then each such threshold couples into a pair of complex valued eigenvalues, which are complex so they are located symmetric with respect to the real part, and with respect to the real axis, both of them are simple, and these are their asymptotic expansions, and we can find this k plus minus explicitly. And these conditions are actually general, because we can first choose and fix W to 1 so that this one is true. Then this sum is fixed. Once we fixed this one is fixed, then this sum is also fixed. And then we just play with the imaginary part, say multiplying it by some constant. And then, of course, we can change W to 1 so that this sum will be greater than this one. And of course, then we shall get this inequality. And in this case, for such model, we shall get exactly the picture which I showed before, that near the threshold, I have one eigenvalue here and one here. And despite the fact that I have just one eigenfunction for this threshold, under the perturbation, it splits into two eigenvalues. So here at the threshold, I have one eigenfunction, and here I have two eigenfunctions, this one and that one. It's like eigenfunction coming from nowhere. And since we have a lunch in 10 minutes, I think I should stop here. Just I should say that if, for instance, these tests don't work, say that the real part is 0, the imaginary part is 0, then actually we are able to find the next terms in these expansions, and then we should make the same tests for the next terms in these expansions. So, but the answer will be quite bulky, and this is why I haven't shown it here.